This is the lesson video for 2-4 Day 3. If you aren't going to be here because of field trip or anything else like that, watch this and use the warm-up front side that we gave you yesterday, and then take notes. So as we go through, you've got 4 things on here to do as warm-up. Pause the video and come back after you're done. If you're back, that means you've already done this on your own and given it a good attempt, and you're here to see if what you have has things that you need to improve or if you're in good shape. So use this, pause the video where you need to. You need really clear communications when you're trying to justify that something's continuous or something has a tangent or has a slope for a tangent. So for number 1, we could talk about the different pieces. X squared is continuous, but again, give a reason. All polynomial functions are continuous, meaning over the reals. 1 over x is continuous over its domain. Therefore, since f of x is the sum of continuous functions, f of x is continuous. You want to be that clear what you're talking about. For number 2, I can't make that the sum or the difference, but I could talk about first what's under the radical sign as a different function, so I renamed it g of x, assigning that sine of x over x squared plus 1. And I can argue that that's continuous as the quotient of 2 continuous functions. Sine of x is continuous, and x squared plus 1. Both are continuous for their entire domains, meaning all reals. H of x then is the square root of x. I'm going to make a composition that represents my original f of x function. So I've got to prove that h of x as on its own would be a continuous function, and then show the composition. So f of x is equal to this composition h of g of x. So f of x is continuous because it's a composition of continuous functions. You need to be that explicit in your justifications as you're writing, so start to challenge yourself to do that. Be specific. Pause this video wherever you need to enhance your warm-up sheet to have better answers. 3, some synonyms. There are several. You had them on notes from the previous day. You could look to see that there are many names for slope of a tangent line. A few I probably don't even have up here. And finally, to have a slope of a tangent at a specific point, 2 things need to be demonstrated. A function needs to be continuous at that point, and then in green I'm reminding you what that means and what you have to demonstrate to say that a function is continuous at a given point. And the slope as both sides approach your x values need to be converging onto the same number. So again, pause video here and add the things you need to add to make your answers things you can refer to and use in the future. Then we're just going to clean up some ideas and show some ways to calculate a little bit faster when you're doing all these things, so no real new content. Review-wise, we just mentioned this, what must be true for a tangent line to even exist? So, some things where you've got examples of where it would not. So for instance, this right here is a cusp, but you can't just say because there's a cusp at a equals 0 that that's why our tangent does not exist. You need to tell what that breaks about the definition of having a tangent line. So something like the slope as x approaches from both sides of A must be equal. And what I'm noticing here is that every tangent line I put into this curve is going to have a slope that's negative, and every tangent line I put in as a slope to this curve is going to have positive, and the slopes here are small. Maybe the slope is 1/2, but then the slope here is getting bigger, and the slope here is getting bigger. So your slopes are actually approaching infinity here. So as x approaches 0 from the right, your slopes are getting bigger and bigger. Whereas as x approaches 0 from the left, your slopes are getting, and you'd say more negative, they're heading towards, so -5, -6, -7, they're heading towards negative infinity. They're not heading towards one another. In the center graph, the problem is that you've got 2 real issues, but the first problem is that the function must be continuous at A. You have a jump discontinuity here, and therefore there cannot be a tangent where the function doesn't even have continuity. And finally, as I look at this last one, at that point that now I made really tiny, at that point we would meet the definition of having a tangent exist, because we could demonstrate that this function that's in green is continuous at that point, again, because the function's value matches the limit as x approaches that value from both the left and the right. And we know that the slopes of those as they're approaching are approaching 0. So as I approach on that curve, that would appear my slopes start very steep, but they are getting flatter and flatter as I approach that point on the curve. You're going to come across problems where they ask you to calculate instantaneous rates of change at different times with a position function given to you, position of where an object is. And you have two ways you can approach these, but I think I'm going to make an argument for the second way. The first way you can approach is to calculate the limit of the difference quotient at every single time they ask for. So in other words, do this for time of 2, time of 3, time of 4, and time of 5. And that's going to get old very quickly, but you do need to at least have a sense of what that might look like. So we'll start that for when t is 2. And you'd be going through the algebra to show that the limit is the distance between 2 points. All right, we'd be looking for what's the function's value at 2 plus h. So at 2 plus h, we'd be at 2 plus h cubed minus 1, minus the function's value at 2, which would be 2 cubed minus 1, all over, eventually we know that that just drops to h, x plus h minus x. And as you go to work this out, I want you to actually pause and do all the algebra so that you're not coming back later and saying, I didn't know how to do that, because you did. I would take this over on the side and work out your cubic. Okay, very carefully making sure you distribute or account for that subtracting of that. And come back to this one. When you are done, you should end up with, and we'll show you what that work would look like in a minute, you should end up with 12. And then you need to go repeat for time equals 3, time equals 4, time equals 5. And that's not going to be a small amount of work. Okay? That's going to be a fair amount of work even for 2, and therefore we're trying to find a way to do this more quickly. And I will show you all that work worked out, so I'd like you to pause the video and actually make yours work so that you can get all the correct notation and things to get that down to 12. If you're back, then you've already done that, and you're looking for a way to calculate a generic formula so that you could use the formula 4 times and not have to do the difference quotient 4 times. To do that, we're just going to pick a letter. I picked A. So instead of 2, 3, 4, and 5, I'm going to calculate the difference quotient at a place x equals A, or at time equals A. So my ordered pairs are really going to be A and A plus H. I'm going to do that generically and set that up so that I can come up with a formula that I can use 4 different times to find the instantaneous velocity or rate of change at those different t's. So my difference quotient with A plus H and A would be A plus H quantity cubed minus 1 minus, and then it'd be A cubed minus 1 for H. Again, pause the video, take that over on the side, work that all out until you can come down to the limit equaling the value of, it's going to have some a's left in it. You're going to come up with a formula of 3a squared. When you do, that's going to be your generic formula that I can put any time into. Then I can actually say, okay, for different times, what's my instantaneous rate of change? So for a time of 2, my 3a squared value would be 3 times 2 squared, 12, which is what we got by doing the difference quotient right away. Then I can plug 3 into that formula, and 4 and 5, and only do difference quotient once. So pause the video here, work that all out. This limit as h approaches 0, this whole thing, cleaning up your algebra nicely and neatly, you need the practice. Then come back. Once again, if you're back, it's so that you're checking things that you did accomplish. It's going to take a little work. So I'm moving mine up so you can see all my work. You can pause it here so that you can check what you got. You can check for mistakes. Again, got through the algebra. That isn't the calculus where you're getting hung up. Okay? When you're done from this screen, then move on. Right, another similar one. So I would approach this the same way. If I need to find how fast the rocket's moving at all those different times, I really do not want to run my difference quotient 4 or 5 different times. So my plan is to come up with a generic formula that lets me do that. So I'm going to go for, instead of 10, 20, and 30 seconds, I'm going to go for a generic formula at A. So my 2 ordered pairs then are at time A and at time A plus a little bit more so that I can work out that generic formula. So I'm going to be looking at the limit of h approaches 0 of, and I know that when I put a plus h into that formula, it's going to be 3a plus h quantity squared minus, and then it'll be 3a squared So there's my difference quotient. Again, showing really good algebra. Since I'm starting with a limit, I need to bring that down. So I know that that's going to be 3a squared plus 6ah's. And again, please go work that out on the side so that you're not asking me how to get that. You know how to get that. Multiply it out by FOIL first and then triple everything that you get. H. I can see right away that my a squareds drop out, which is lovely. I'm going to divide an a out so that I end up with the limit as h approaches 0 of 6a plus 3h. Then I can go to direct substitution of my 0, and I'll get 6a plus 3 times 0, or a generic formula for this situation of 6a. Then for 10, 20, 30 seconds, my time, and my 6 times that time. Okay, so times of 10, 20, and 30 seconds, I know I can go over and calculate. And maybe what I should say here is that at a generic time, instead of t, our generic time is called a, and the formula is 6a. So then this would be at 10 seconds, our rocket would be going 60 feet per second. At 20, it would be going 6 times 20, 120. And at 30, 6 times 30, 180. And these would all be in feet per second as your instantaneous speed or rate of change. Again, stop the video, gut out the algebra. Then they might get into volume ones. So the volume ones that you might be seeing, and ignore that, it was trying to put in a little GeoGebra one that I hope you saw, because it actually had some kind of cool stuff, is it had the formula for the volume of the solid. So we'll give that one to you. So the volume of a sphere is 4/3 pi times radius cubed. And they would like to know that instantaneous rate of change at different times. Okay? And as the radius gets bigger, the volume does not get the same amount larger because you're adding a lot more volume as those radius inches get bigger. So you'd want to find a way, again, to calculate that difference of the limit formula. But again, I'm going to use a's instead of all those different r values. So my two order pairs be a and a plus h. So I'd be looking at 4/3 pi a plus h cubed minus 4/3 pi a cubed all over h. And as I start to work that out, and again, multiply everything out, go over on the side, pause the video, make sure you can do that. Okay, my a plus h quantity cubed is really a cubed plus 3a squared h plus 3ah squared plus h cubed. Okay, that's all that, minus my 4/3 pi a cubed. Okay, so as I do that, all over h. Again, pause video to clean up what you may need to. You can distribute the 4/3 or keep the 4/3 not distributed. Right away in the first term, that's how you could get rid of that last term, and therefore that would go away. So I'm going to keep my 4/3 not distributed, just in the interest of my own sanity. Okay, then I can divide by h. I can factor my h out still so that I have one that's a little bit easier to use. And so in factoring that h out, the h would just come out in front, and then I could divide that all out. So I'm going to have 4/3 3a squared plus 3ah plus h squared. As that approaches 0, lost my pi there, sorry. As that approaches 0, then I'm going to get 4/3 pi times that's going to become 0, and that's going to become 0, so really 3a squared in there. When I clean that up, the 3's divide each other out. 4 pi a squared then is my generic formula. Then I can use my generic formula to go back up to time 2, 3, 4, and 5 and find what I need. Be sure to finish this one. Finally, tonight's assignment, the 2-4 day 3. Then the next days, just in case you're curious, 2-4 day 4. You have a quiz 2-3, 2-4 on Friday, and your chapter 2 test is next week, Wednesday. We do not have school on Monday.